projects. In this video, we are going to explain about the project, which is SuperYOLO, Super Resolution Assisted Object Detection in Multimodal Remote Sensing Imagery. Introduction of the project. The project addresses the challenges of accurately detecting multi-scale small objects in real time, particularly in time-sensitive scenarios like military reconnaissance and emergency rescue using remote sensory imagery, which is RSI. Over the decades, deep neural network-based object detection frameworks has evolved significantly with a focus on enhancing accuracy through the use of large-scale, natural datasets with precise annotations. RSI introduces unique challenges including a limited number of labeled samples, small object sizes, and diverse object scales with multiple categories. The project emphasizes the need for improved object detection techniques tailored to the characteristics of RSI. The project proposes the method, named SuperYOLO, focuses on enhancing detection capabilities by fusing complementary information from multimodal images. Unlike many existing solutions that rely on complex deep neural networks, SuperYOLO aims to achieve higher accuracy while minimizing the computational burden. Objective of the project. The primary objective is to improve the accuracy of small object detection in remote sensing imagery, which is RSI, by introducing a novel method, SuperYOLO, that effectively fuses multimodal data and employs assisted super resolution learning. The project aims to achieve real-time small object detection capabilities, specifically catering to time-sensitive tasks such as military reconnaissance and emergency rescue operations, where quick and accurate identification of objects is crucial. The objective is to include addressing the computational challenges associated with small object detection by designing a compact baseline, SuperYOLO, that minimizes the heavy computation burden typically associated with complex deep neural networks without compromising accuracy. To enhance the detection capability, the project focused on the fusion of complementary information from different modalities using pixel-level multimodal fusion, which is MF. The objective aims to exploit diverse data sources for more effective and suitable feature extraction. The project seeks to find an optimal balance between accuracy and speed, offering a favorable trade-off. SuperYOLO is designed to provide a competitive accuracy compared to state-of-the-art models while maintaining a more efficient computational profile, making it suitable for real-time applications. To implement this project, we need software and hardware requirements. Coming to hardware requirements, we need operating system of Windows, processor of i5 and above, RAM of 8GB and above, and hard disk of 25GB and above. Coming to software requirements, we need application of Anaconda, primary language of Python, front-end framework of Flask, back-end framework of Jupyter Notebook, database of SQLite 3, front-end technologies of HTML, CSS, JavaScript, and Bootstrap 4. To implement this project, we have designed various steps in the flow of work. The first step is importing the packages. This step involves importing necessary Python libraries and packages that are required for image processing, machine learning, and web development. We have imported NumPy for numerical operations, OpenCV for image processing, TensorFlow for deep learning, and Flask for web development. The next step is exploring the dataset. Here we have some steps. Reading the image involves loading an image file into the program using OpenCV. Plotting the image using libraries like Matplotlib, providing a visual representation of the dataset. The next step is image processing. Here also we have substeps. Converting to a blob object is common in deep learning to prepare images for input into neural network. Defining classes involves specifying the categories that the model will detect, and bounding boxes are the coordinates outlining the detected objects. Converting the array to a NumPy array facilitates efficient data manipulation. The next step is loading the pre-trained model. Here also we have such steps. Reading the network layer involves loading a pre-trained model using a deep learning library like TensorFlow. Extracting the output layers is crucial for obtaining predictions from the model. The next step is image processing. Here we have substeps. Appending the image and dealing with the annotation files are common steps in preparing dataset for training. The next step is converting BGR to RGB, which is blue, green, red to red, green, blue, is necessary in certain cases as OpenCV often reads images in BGR format. Creating a mask and resizing the image optimizes it for input into the neural network. The next step is data augmentation. Randomizing, rotating, and transforming the images are the techniques used to artificially increase the diversity of the training dataset, improving the model generalization. The next step is building the model. This step involves constructing the deep learning model architecture. The next step is training the model. The model is trained on the pre-processed dataset, adjusting its weights and using optimization algorithms. The next step is Flask framework with SQLite for sign-up and sign-out. Flask is used to set up a web application, and SQLite is employed as a lightweight database for user authentication. Routes are defined for sign-up and sign-in. The next step is user gives input as image or video. User interact with the web application, providing input in the form of an image or the video. Pre-processing and model inference. The input image or the video is pre-processed using the techniques developed earlier, and the trained model is used for detection. Object segmentation and bounding boxes. The model's predictions are used to segment objects in the input, and bounding boxes are drawn around the detected objects. The next step is final outcome is displayed. The final result with the segmented objects, algorithms which are used in this project are YOLO V5S, which is YOLO V5 small. You Only Look Once, which is YOLO, is a real-time object detection system that divides an image into a grid and predicts bounding boxes and class probabilities for each grid cell. YOLO V5S specifically refers to a smaller variant of YOLO designed for faster inference and lower computational requirements. It optimizes for real-time applications with reduced model size. It is chosen for scenarios where real-time object detection is crucial, such as military reconnaissance and emergency response. Its smaller size makes it more suitable for deployment in resource-constrained environments. YOLO V5M, which is medium. Similar to YOLO V5S, YOLO V5M is a medium-sized variant of the YOLO object detection. It balances between speed and accuracy, making it suitable for scenarios where a compromise between model size and detection performance is desired. It is chosen when a trade-off between detection accuracy and computational efficiency is needed. It provides a middle ground in terms of model size and performance. The next algorithm is YOLO V5L, which is large. It is a large variant of YOLO designed to achieve higher accuracy. It utilizes deeper and more complex architecture compared to small versions, providing improved detection capabilities at the cost of increased computational requirements. It is employed when the project demands a higher level of precision in object detection, even if it requires more computational resources. The next algorithm is YOLO V5X. It represents the extra-large variant of YOLO, featuring a more extensive and sophisticated architecture. This variant is designed for tasks where maximizing detection accuracy is a priority and computational resources are not a limiting factor. It is chosen when the project requires the highest level of detection accuracy and computational resources are not a limiting factor. YOLO V3, which is You Only Look Once version 3. It is an earlier version of the YOLO object detection system. It utilizes a grid-based approach to predict bounding boxes and class probabilities efficiently. YOLO V3 is known for its balance between speed and accuracy, and it is suitable for various real-time applications. It is considered for its balance between accuracy and speed, particularly in scenarios where the latest YOLO V5 variants may not be necessary for beneficial. YOLO V4, which is You Only Look Once version 4. It is an upgraded version of the YOLO object detection system, introducing features like CSPD Darknet 53 backbone and PANet to enhance accuracy and efficiency. It is designed to push the boundaries of the object detection performance while maintaining real-time capabilities. The next algorithm is SuperYOLO. SuperYOLO is a term specific to the project. It is a variant of YOLO designed for accurate and fast small object detection in remote sensing imagery. The algorithm incorporates multimodal data fusion and assisted super-resolution learning to optimize the detection of small objects while considering computational efficiency. It is tailored to the unique requirements of the project, aiming to excel in small object detection in remote sensing imagery while optimizing for speed and efficiency. As an extension, we have used other version of YOLO to improve the detection accuracy, and also as an extension we have built frontend using Flask framework for user testing and authentication. We have evaluated this project using different error metrics, which are precision, recall and map. Here we have precision score comparison graph. On x-axis it represents precision score for each algorithm, and on y-axis we have algorithm names. Precision is a metric that measures the accuracy of positive predictions made by a model. It is calculated as the ratio of true positive predictions to the sum of true positives and false positives. This is recall comparison graph. Recall is also known as sensitivity or true positive rate. It measures the model's ability to capture all relevant instances of a class. It is calculated as a ratio of true positive predictions to the sum of true positives and false negatives. This is MAP, which is mean average precision. It is a metric commonly used in the object detection task. It calculates the average precision for each class and then takes the mean across all classes. Average precision in turn is the area under the precision recall curve. The algorithm which performs well among all these metrics will be used for final prediction. To execute the project, first we need to open the code folder which contains source code files. This is the code folder of the project. This is the static folder, which contains files related to CSS, JavaScript and Bootstrap files. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, etc., which represent different pages of the website. Here we have app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content that to be rendered in the HTML templates. Here we have dataset folder. We use this dataset for training the algorithms. This is the sign-up file. This file is the database file used to store the user information. This is the notebook file. It is a Jupyter notebook file which contains a combination of code, graphs and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for the data science. Now we need to copy the path of the code folder from the address bar of the file explorer. So I'm copying the path. Now we need to open the Anaconda prompt. Using the cd command followed by the space, we need to paste the copied path and then click on enter. Here we can see that current directory is changed to the code folder's path. Here we need to type the command python space app.py and click on enter. This will compile app.py file and this command will execute the Python script and perform a runtime check for any syntax errors or logical issues. After running the app.py file, Flask framework will host the application locally at the default address, which will be the localhost and the port unless configured differently. This is the localhost and this is the port. Now we need to copy this local link provided by the framework and paste it in any web browser. So I'm copying the link. I prefer Google Chrome, so I'll paste it in that. Here we need to paste the link and then click on enter. This is the web page of the project which is displayed in the browser, and this web page is built by using the Flask framework. Here we can see a sign up link. First we need to click on that and enter all the sign up details if you are signing up newly. I have already signed up, so we'll directly click on login. Here we need to provide our credentials, which are the username and the password. So I have given the username and the password. Now we need to click on login. We have logged in successfully. Click on choose file button to upload any image. So I'm clicking on choose file button and selecting the first image. Now we need to click on open. Click on upload. Here we can see that small object which is truck has been segmented with the bounding box and with the probability score. Now we will upload one more image and see what will be detected. Click on choose file. So I'm selecting this image this time. Click on open. Click on upload. Here we can see that port has been segmented with the green color, car, pickup points, that's it. And we have also probability scores and the bounding boxes for that particular objects. Now we will upload one more image and see what will be predicted. Click on back arrow, click on choose file, and now we'll select this image. and click on Open. And now click on Upload. Here we can see that nothing has been identified. Now we will upload one more image and see what will be segmented. Click on Choose File. And selecting this image, click on Open. Click on Upload. Here we can see that two objects has been identified, which is truck and the car. In this way, if we upload images to the system will segment the object and identify with the bounding box. Now click on Sign Out. Conclusion of the project. The project successfully utilized pixel-level multimodal fusion techniques, allowing the model to extract valuable information from various data sources. This approach facilitated the generation of more robust and effective features, particularly beneficial for small object detection in remote sensing imagery. By considering the computation cost, the project implemented strategies to balance accuracy and speed in object detection. Techniques such as model simplification and efficient architecture design were employed to achieve real-time detection capabilities, crucial for time-sensitive applications like military reconnaissance and emergency rescue. The project's findings emphasize the extension algorithm effectiveness in rapidly detecting small objects in real time. This bears substantial significance for prompt decision-making in military and emergency response scenarios. The project's outcomes suggest that the proposed methodologies and models are well suited for time-sensitive tasks. The ability to detect small objects accurately in real time, as demonstrated in the project, has significant implications for applications require quick and precise decision-making such as military operations and emergency response.
Thank you for watching video. For more projects, please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.